Oh, hey, Madison.
Hello.
Hi. Did you have to be let in?
No, I don't think so.
Oh, okay. No, you must have just joined right when I started it because it was saying someone was in the lobby. Okay.
Oh, yeah, I got back from the meeting. Walked over here real quick. Okay.
Hmm.
All right, it's that 3 o'clock time. Any announcements, things that y'all want to do?
We're good over here, so whenever you're ready to take over, thank you.
Right, fantastic. All right, so it is Monday afternoon at 3 o'clock. So we're going to go ahead and start the exam to review for spring 2025. So first thing that I have up here is this notion of what sections are covered. So this is something that actually got posted to the 701 section a while ago. It's like February 22nd is when this was posted. But what this shows is the sections out of chapter 14. So this is the part that involves reaction mechanisms, catalysts, intermediates, elementary steps, things like that. Chapter 16, which is where we've spent a fair amount of time, especially last week, had to do with equilibrium, writing equilibrium expressions, doing equilibrium calculations, things like that. And then the chapter that I know I really mostly started today, chapter 17, which is acids and bases. So in 14, it's just 2 sections at the very end, and there are, I pulled the end of chapter problems that relate to those sections. Chapter 16, your end of chapter problems are just whatever is listed. They're end of chapter problems, I'm just going to say as listed, because even though we do take out one particular section and move it, we actually already did that in the end of chapter problems. So that's actually already noted. Also, essentially, what chapter 16 usually looks like is, I'm just going to say it's all the notes. Because I think all 3 of us as instructors have our notes for chapter 16 done to include everything. And I think the little piece of 16.4, I think we all just tuck into a later chapter. So there are times where we move a small piece of information, and usually, unless you're actually comparing it to the textbook, you don't actually notice that we moved it because it tells a better story somewhere else. So it is all the notes, no changes there. Chapter 17 is acids and bases. The big weird thing with this is where we stop is kind of strange according to the book. And we can have this conversation. So basically where we stop in the book is, it says through 17.7, but really what that actually is going to include is that really is going to be 17.6 and 17.7. It says to exclude the ice table calculations for weak acids, weak bases for this exam. What that really means is for 17.6 and 17.7, we want to include definitions of Ka and Kb. So that's going to be equilibrium constants as applied to acids, equilibrium constants applied to weak bases. And I'm going to put acid base strength. And we can certainly talk about what that means. That is basically the very tail end of what we're going to cover before the exam. So that's kind of strange because there are calculations in 17.6 and 17.7. We're going to save the calculations for later, but there's things we can do with the equilibrium constants because it applies really beautifully to things we did in chapter 16. We can certainly take a look at that if y'all want to. So a reminder, you guys should be able to drop questions into the chat. I have a couple prepared for you guys already, which is what I will go ahead and start with. But I just want to point out we've got this information and some end of chapter problems to go with chapter 17. And all of this I posted to the 701 section like 2:30, because that's when I got around to it. Potentially useful information. I'm going to check with Dr. Diekman and Dr. Bacone tonight to see if there's anything to add to this. So this is actually the one that y'all already have posted, but something I want to point out is there's already on here a chapter 16 equation, which is the Kp to Kc equation. And there's also already this lovely set of pH, pOH, Kw, and pKw. So on the previous exam 1, potentially useful information, there was already some chapter 16 and some chapter 17 stuff already on there. So again, I'm going to double check with Dr. Diekman and Dr. Bacone to see if there's anything else we're going to add or modify, but we may very well be using the same potentially useful information on this exam as we used on the last exam. So I will get some clarity on that for y'all, just so you know. But want to point out that some of that stuff is already there. And I grabbed a periodic table just should we need it. So I am just going to go ahead and start with this question because I've got this one prepared. while I'm going to assume questions are coming into the chat because I'm seeing people come in a little bit by bit. So this says for the reaction below, which yes is written by hand so that I can write in those equilibrium arrows, if Kc is equal to 0.9 and the initial concentration of HI is 0.02, what's the equilibrium concentration of hydrogen iodide? So this is going to be an ICE table question. So when we talk about ICE tables, so that is the acronym where we basically put I, C, and E here on the left. The I stands for initial, the C stands for change, the E stands for equilibrium. In a question like this, what they're trying to tell you is that we have an initial concentration of HI, which is this thing right here. But that's the only thing that's mentioned. Since that's the only thing that's mentioned, I'm going to assume that the concentration of my other two species are 0. And then from this information, I should be able to calculate the question, which is what is the equilibrium concentration of hydrogen iodide at the end. So that's what we're looking for. So a few things. So first of all, when we actually look at what's happening here, what you might notice is I have zeros actually for my reactants. If I wanted to, I could go ahead and calculate what we refer to as QC, which is going to have the same general expression as K, but now what I would do is go ahead and say, well, now I have my products divided by my reactants. And we can't really divide something by 0, but essentially when you divide something by 0, we can say that it's ridiculously large. I know we could have a lovely discussion about the mathematics of dividing by 0, but we're just going to say that we are dividing by 0 here, and so we're going to say that this is more or less infinity. This is super large, really big. Or another way to say that is that I have too many products. So one of the questions that I got asked was, how do I figure out which way the reaction is going in something like this? And one of those answers is to calculate QC. So if I actually had numbers for everything, I could go ahead and calculate Q and figure out what's going on and where my reaction is going to go. The thing though here is that I don't, since I have zeros for some of these, the other thing I should know is I should know that I shouldn't wind up with anything negative in the end. So everything in the equilibrium row here must be positive. We can't have negative molarities. We can't have negative pressures. So since I already start with 0 and my change row is going to just add to my initial, those things have to be positive so that I have positive things in my equilibrium row. So that means I'm going to subtract from whatever I already have. So 0.02 minus 2x. So what I'm doing in here is I'm essentially adding together my initial plus my change. So I also could have written here 0 plus x, 0 plus x, if that makes that easier to think through. So as we're going through, what we're trying to figure out, first of all, was how do we know what the signs are in the change row? We know what to do in the change row because we know which direction our reaction is going. I know which direction my reaction is going either because I have zeros in my initial column, and wherever I have zeros is where I have to have something positive. So wherever I have a 0 is where I have to have something positive. Wherever I have a 0 is where I have to have something positive. I don't get to have negative values in my equilibrium table. So that's how I knew to put positives on the left and the negative on the right, is because I'm putting positives wherever the zeros are. I'm also making a claim then that this reaction overall, in this case, is going to go back to the reactants. Again, because of where these zeros are located. That's how I know. It's because of where the zeros are located. So that gets us an ice table. Now the next question is actually doing the solving. When I look at actually solving this particular problem, one thing that I want to be able to do is look at my value of K and look at my value of my initial concentration. And one thing I can see without doing any other math is K is larger than my initial concentration without doing anything to it. So one of the things I was talking with my class about is that I could take 400 times my K value and compare it to my initial concentration. If this is larger, then we have to use either a perfect square or quadratic. We can't use the approximation method when the K value is too big. So our K value is in fact going to be too large. So we are going to need to go ahead and solve for this using either perfect square or quadratic. I've got a K value. My K value is 0.9. That K value is equal to, I'm going to go ahead and put in my concentrations, products over reactants using exponents, using the coefficients as exponents. So I'm just going to go ahead and write my K expression in here to have that good practice. So I've got my K value from the problem, my 0.9, and then I've got everything, I've got my expression. So now I can go ahead and plug in because that equilibrium row in red should be equal to my value for K. So now I've got my HI, 0, 2 minus 2x all squared. So I got a squared term here, squared term there, all divided by basically x times x, or to write that a little bit differently, x squared. Also super glad I got my reunited with my pen. From here, what I can actually see is that because I have this is squared and that is squared, I can actually do a technique referred to as the perfect square. So what that means is I can actually take and just square root my 0.9 and I can square root my entire expression. So when I do that, take 0.9 and take the square root of that, I get 0.9487 is equal to, and all I'm doing now is taking the square parts away. So from here, I just need to solve for my algebra. So I'm going to multiply both sides by my x. I get 0.9487x is equal to 0.02 minus 2x. Then I'm going to go ahead and add 2x to both sides. So one of the other comments that I got was basically talking about doing the algebra. This is the part where practice is really helpful. So practicing what all you need to do can be very, very helpful. And then here we're just going to divide both sides by the 2.9487, divide by 2.9487. Just make sure we're dividing by the same thing. And I get a value of x of 0.00678. Now, one of the things I definitely want to do, one, I do wish that I had had time to double check. That looks good. I do wish I'd gotten to do all this math beforehand. So because this is my value for x, it's really tempting to say that this is my answer, but I need to check the problem to remember what I'm solving for, what x is, or what I'm solving for. Because this is x, but maybe that's not the answer to the problem. So we're going to take this all the way back, all the way back, all the way back to my equilibrium table. And the question actually wants to know the equilibrium concentration of HI. And we actually had put a box around it. I'm going to put that box around it again. So this is actually what we wanted to solve for. We actually wanted to solve for that thing. It's 0.02 minus 2x. So that was actually the goal of what we're solving for. So since 0.02 minus 2x is our answer, now I can go ahead and plug that in. 0.02 minus 2 times 0.00678. So this is all part of that problem solving. 0.02 minus 0.01357 get something like 0.0064 molar. So that problem took us, what, about 10 to 12 minutes? So one of the things in doing ICE table problems, one, talking through them does take longer, but two, is also practicing so that you can go about them relatively quickly, and practicing everything so that you got time to do the couple of ICE table problems, because they can be longer problems, and they can be longer problems in general when we think about those. Okay, so now that I've done a problem, we've let people get in a little bit. Are there any questions in the chat so far?
There's only one that I see. It is, could you go over the stuff that are true and not true of a reaction at equilibrium? Jeez.
Okay, we can definitely talk about that. If you saw my face a little bit, so one of the things about this, this is a really common. So one thing to keep in mind is whenever you ask me for things that are false at equilibrium, there are some things that are common misconceptions, and those are the ones that I'm going to mention. I could tell you lots of false statements about equilibrium, like you have to have a parade of elephants go by to have equilibrium, and that would also be false, but you would know that that's false. So keep in mind that I'm probably going to miss some false statements in here because there's technically an infinite number of false statements to make. So I will do my best on this one, but just keep in mind that I don't entirely know what all you might want on that one, because there is no perfect list of true false statements about equilibrium, but there are a couple things that often come up. So taking this one out of the notes. So something to keep in mind whenever we're talking about equilibrium is where, and on the graph here, you can argue exactly where this is. I'm going to say it's about here. Equilibrium is where the concentrations are no longer changing. That's a true statement. So wherever on my graph where I'm looking at reactants and products, where I can start to say that the concentrations don't change anymore. The concentrations themselves are stable. The concentrations themselves do not change. The concentrations stay. That's equilibrium. Now, because this is my true statement, there are some things that sound like they are the same thing, but they're not. So the true statement is concentrations are no longer changing at equilibrium. So concentrations are no longer changing at equilibrium. That's the true statement. Some of the things that are false, and we're going to do false in red. So some of the things that are false, but sound like it might be similar. The false statement is something like concentrations must be equal. This is a false statement. You can actually see it here on the graph. Here is one concentration up here, and here is the other concentration down there. They're not the same. They did not come together in one line. Not the same concentration. But it sounds good, but it's wrong. Concentrations of products and reactants do not have to be the same at equilibrium. Concentrations of, you have two reactants, those don't have to be the same at equilibrium either. There's lots of different possible combinations of concentrations that can get you to the same answer for equilibrium. But concentrations being equal is one of our kind of common false statements. Another false statement over here going along with the true statement that concentrations are no longer changing is that the reaction stops at equilibrium. This is a common false statement. So the thing is that the concentrations aren't changing anymore, and that's true, but the reaction itself doesn't actually stop happening. This is part of the reason why when we represent equilibrium, we represent it with those equilibrium arrows going back and forth. So if I have in my container, if I have two molecules, we'll give it 3 molecules of A and we'll give it 1 molecule of B. If one of my molecules of A just then reacts to become a molecule of B, and now I have my molecule of B where I once had my molecule of A, what we kind of assume then is that one of the molecules of B is also changing into A. So I know my picture's maybe not so great, but basically what we assume is happening is that there's a constant change happening. Hold on. There's a really lovely PET simulation I actually really like. I don't want to download Java, thanks. So I actually usually use this one a little bit later. That'll be fine. So this is going to let me drop some ionic compounds into water. And when it does that, I get all these little dots. And if you pay attention, you can kind of see on the outside edges that I'm getting some of those ions, because that's what they're supposed to represent. I'm getting some of the ions to actually go ahead and come back into this crystal shape. So that's supposed to represent them becoming a solid. But whenever that happens, there's also times where some of the other ones detach and go back into solution. So I have this idea where I have more or less the same number of ions hanging out in solution and the same number of ions that are stuck in the lattice, but the exact ion, like if I could label each one of these, or if I could name each one of these, the exact ion isn't necessarily always stuck in that structure. Sometimes it is stuck in the structure and then it becomes dissolved and goes and it hangs out and floats around or goes back. You can even kind of watch, if you watch it for long enough, some of these are like sticking to the bottom. So they're not necessarily having to be in that lattice together. So there's an idea we refer to as dynamic equilibrium, which basically is trying to say this idea that things are not actually changing. So the reaction stops at equilibrium is also a false statement. Even though the concentrations are no longer changing, the reaction itself is still going on. It's still happening. What else about equilibrium can I say that's false but sounds really, really good? Hold on just a minute. Sorry, it is spring and allergies have started. That's what I want to say about that for right now. Let me go ahead and grab another graph so we can talk about this one. So as far as things that are true and things that are false about equilibrium, this graph is now actually trying to talk about the rate. So this thing on the axis here is the rate. So again, the thing that is true at equilibrium is that the forward rate is equal to the reverse rate at equilibrium. That's the true statement. And oftentimes when we want to talk about false statements, when we deal with the rate, either we want to talk about the same thing we did before, which is a false statement. We'll make false red again. A false statement being something like the reaction stops. A false statement being something like the reaction rate depends on a catalyst, which this one is false for equilibrium, because the thing is that we don't care about catalysts in equilibrium. We care about catalysts for reaction rates, but we don't care about catalysts in equilibrium. So the reaction rate does depend on the presence of a catalyst, but equilibrium won't change with the presence of a catalyst. We could also talk about reaction rate depends on a value of Kc. Also a false statement. That value of the equilibrium constant is not connected to how fast the reaction goes. So hopefully these give you some ideas about values, about equilibrium itself. We could also talk about things like K and Q. So I'll just put in here that, again, the true statement, which is that K and Q should be equal at equilibrium. So I'll put that one in there. Another true statement about equilibrium is that K is temperature dependent. So those are all things that can go with true statements about equilibrium. If you guys have any questions about why those are true or why the false ones are false, then let me know. I tried to color code those as we went along. So your false statements are in red, but your true statements are in black. So hopefully that's helpful in that. Okay. So what I'm actually going to do is prepped another question. So kind of while you guys are potentially putting in other questions, I'm at least going to copy over and make pretty another question. So basically stalling for time just a little bit, because this doesn't actually look, this has a question mark in it, but I was going to actually go ahead and write this out. So given the reaction and an initial concentration of A being equal to 0.75 molar, Kc is 1.9 times 10 to the negative 10. what is the equilibrium concentration of B? So before I do another math question, are there any other questions from the chat?
Yes, there's actually quite a few now.
Oh, fabulous. Great.
Okay. So, second. Okay.
Let's go.
Are you ready?
Yep.
All right. Can you do an example of an approximation problem?
Yep.
Could you go over an equilibrium concentration question where all initial values are given?
Sure. Okay.
Can you explain Le Chatelet principle when it comes to change in temperature?
Okay.
Can you go over how to determine changes in composition and shifts in equilibrium?
Okay.
Do you mind explaining elementary steps and telling the difference between catalysts?
Okay.
I believe that is everything for now.
Oh, great. So since the question that I wrote in blue is an we'll answer at least one of these questions. I'm going to go ahead and do that one. I will just move it because it has all my lovely A's and B's. There we go. To deal with. Okay. So I have 2A is in equilibrium with 3B plus C. I've got an initial concentration of A, a value of Kc, and it's asked what is B. So what I'm going to do first is I'm going to go ahead and set up my ice table. So I have my 2A is in equilibrium with 3B plus C. I should have given all of these state symbols. We'll go ahead and make everything aqueous just to make my life a little easier. Aqueous, aqueous. Then I have an initial concentration on my ice table of 0.75 and nothing else. So this is another time where we're going to go where the zeros lead us. So I should have minus 2x plus 3x plus x. So then my equilibrium row is 0.75 minus 2x, 3x, and x. Then from here, I can grab my value of Kc, 1.9 times 10 to the negative 10. And again, we're going to go ahead and fill out and practice our K expressions. So that's the concentration of B cubed, so my products, using the coefficients as exponents, all divided by A squared. Then I can go ahead and plug in. And this is where, so there are a couple of different, when we talk about the approximation method. So now I've got B is 3x, that is all cubed, times x divided by 0.75 minus 2x, and that is all squared. So when we talk about the approximation method, I am using this little rinky-dink calculator. I'm not using a graphing calculator. I'm not using a graphing calculator for a couple of reasons, but basically a graphing calculator is not required for this course. So I am not going to use a however the heck much those costs when this $20 calculator. I'm confused about how much it costs because in the summertime these usually go on sale, and that's when I buy them. Also, I don't know if you guys have ever looked at these prices, but sometimes on Amazon, like what color this is will change how much it costs, which is weird to me. Anyway, So I have some options for solving. But one of the things to keep in mind here is I can't use the quadratic. It goes too high. Because I'm going to get 3x cubed, 3x all cubed times x, which is going to get me an x to the fourth. I can't use the quadratic. It won't do me any good. Because this is not a squared term. Down here I have something squared. But the top I don't, so the quadratic won't help. So this is basically the time to go, oh no, gosh, I really hope the approximation method is useful. For the approximation method, really what I'm trying to look at is I'm trying to compare before I get started and then after we're done. So this is the hard thing with the approximation method is some people would like a before I ever start, tell me that this will work. Before I ever start, tell me that this will work is asking you to compare a value of K against your initial concentration. Because what you are banking on is you are banking on the idea that while I start with A and I'm going to move to products, that move is really, really small. So that move is so small that you technically won't even notice that it happened. Because we're going to bank on the fact that the change from away from A is incredibly small. So I usually use an analogy. So I already mentioned Amazon with this calculator. Jeff Bezos, founder of Amazon, right? Lots and lots and lots and lots of money. If Jeff Bezos drops $1 out of his pocket on accident, we don't say that his entire net worth has changed by the one single dollar that he dropped, because it just doesn't matter. That $1 is such a teeny tiny portion of his total net worth that it's not even worth recalculating if he accidentally drops $1 out of his pocket. So we would basically say that change is so small that it doesn't matter, that change is in fact zero. So I'm trying to say that this Kc value is so small that my initial constant, the change away from the initial concentration is basically zero. So when I come down and I look at this, what I'm then going to say is I'm going to say that this change here, that my x here is just zero. Where that change is. So then when I go to rewrite everything, 1.9 times 10 to the negative 10 is equal to, I'm going to go ahead and factor this out. This is 9x to the fourth divided by 0.75 minus 2 times 0. I am going to go ahead and put that in red, because this is the assumption we were talking about. This new thing where I've got x is equal to 0. This is the Jeff Bezos loses $1, but we don't care. We don't care about the lost dollar. Doesn't even matter. Being able to say that change is so small that it doesn't matter, now lets me be able to solve the problem. So I still do have to deal with this x to the fourth. I still have to deal with the 0.75 now squared, but now that's just a number. So I can deal with that. So I can go ahead now and turn my calculator back on. So I'm going to square my 0.75 and multiply it times my 1.9 times to the negative 10th and get 1.06875 times 10 to the negative 10. I'm going to double check real quick. Okay, that's why. 0.75 squared is about 0.56. That's why. Just double checking my own math as I go along. And then so I'm trying to get the x alone. I'm going to divide both sides by 9. I get x to the fourth is equal to 1.1875 times 10 to the negative 11. What I am then going to do, and this one is up to you. So on your calculator, there might be this thing where there was a fourth root. Frankly, because of the calculators I use, I just use fractional exponents. So I just raise everything to the 1/4 power, or to the power of 0.25. However, if you can find there is usually a little button that looks something like this. And then what you need to do is take the 4th root to that. So depending on how your calculator works, is how you could solve this problem. I know I am being vague in terms of that. That's because everybody gets to use a calculator as whatever they want, as long as it does not connect to the internet. And I could not tell you what that button looks like on a Casio. I have no idea. So here's my answer for X. Now, what I'm going to go ahead and say is I'm going to say that we went ahead and used the approximation method for 2 reasons. One, because with this calculator that I have, this is the only option I had, number 1. Number 2, because K was small. K was 10 to the negative 10th. That's small. Now that I have a value for X, what I am going to go ahead and do is I'm going to check the 5% rule. When I check the 5% rule, what I'm going to do is I'm going to take the change. I'm going to take X, and I'm going to divide it by the initial concentration, multiply it by 100%, because this is a 5% rule. And what I want is I want that to be smaller than 5%, because again, this is now giving, basically, we use the big analogy of a billionaire, however much money they've got, loses $1. And that is one way to think about it. This is giving you a different value, which is, instead of a billionaire losing $1, this is the change less than 5%? This gives us a little bit more room for error. Your change just needs to be less than 5%. And if the change is less than 5%, we're going to assume that it was small enough that this will then work. So all we're going to do then is take my X value, 0.001856, and divide it by 0.75, which was our initial concentration. Multiply by 100%. Now, one of the questions I usually get is about, like, how close does this number have to be? Guys, we want you to know and be confident in using the approximation. So for that reason, we don't give you guys answers like this that come to like 5.1%. Okay, that's too close. This either needs to be obviously under 5% or obviously over 5%. But I understand you guys get nervous about what happens if it's just close. And I'm just going to tell you that we set up problems so that you don't have to worry about that. So my 0.24 is less than 5. So the change, my X value, is less than 5%. It was technically 0.25%, 1/4%. So since the change value is really small, this means that my approximation is valid. That's what that means. So since my approximation is valid, that means that when I scroll back up to the top, I can go ahead and use that value of X, that 0.001856. So the goal was, what is the equilibrium concentration of B? So my actual question was about the equilibrium concentration of B, which is that 3X. I have already forgotten what X was. Oh dear. So when I actually want to solve for the answer, I want the concentration of B at equilibrium, which is equal to 3X. So therefore, when I'm doing that, I'm going to take that 0.001856 and multiply it by 3. So then I get my answer to be 0.00, let's do 56. So this then is the actual answer to the problem. So we used an ice table. We looked at how small k was. We solved for x using the approximation method, assuming that that change was small. Since we assume the change is small, we went ahead and double checked it with the 5% rule. After double checking with the 5% rule, we went ahead and double checked what the question actually asked for, which in this case was the concentration of B. In our ice table, that was 3x, so we multiplied it by 3. There are a lot of pieces to this question. There are. I know there are. One of the things to keep in mind is while we will ask you guys ice table problems, we will also ask you questions about other things. That's part of why the very beginning of this exam review had that list of all the different pieces that we'll ask you for. Now, a couple other questions that I've gotten from students. I've gotten questions such as, do I have to use the approximation method if I can just use my graphing calculator for everything? So here's a thing I don't know, and this is something that we actually haven't had this conversation a whole lot. This 0.0056 is what I get from this little dinky scientific calculator. I don't know if when you use a graphing calculator, how many more decimal places you have and how far off you are because you used a graphing calculator. Maybe the answer is none. But the approximation method is the approximation method, which means sometimes it's going to be off in the last digit. Usually it's not because, again, that value of k is so small, the change is so small, we use the approximation method because it works. But there are some people that if this very last digit for x that I've got 0.001856, and if your calculator told you that that last digit was a 7, some of y'all can't handle that. That rounding error goes away by the time you actually finish the problem. But for some of you, that's not acceptable. So when the question is, can I use my graphing calculator and never touch the approximation method? I don't know, because it should be fine, but are you going to be okay if the rounding is different? Also, I should say that we have been known to ask about the 5% rule on exams because we taught you the 5% rule. So if your goal is to skip the approximation method and never solve with it, on one hand, that's fine. On the other hand, you'd better be able to use the 5% rule in case we ask you about that. So just do be aware. We have also been known to ask about ice table setup. So just do be aware that we taught it to you. So if we teach it, then we're allowed to ask you questions about it. Because the idea of using an approximation and the equipment that you have over fancier, more expensive equipment like a graphing calculator, we are allowed to ask you about the problem solving methods we taught. We all taught the 5% rule. At least I assume we all did. I did. I should say I did. So hopefully that helps with that one. So there's an approximation method. One of the other one is doing equilibrium concentrations when all of the initial concentrations are given. Yes. Yes. So there are two different ways. There's two different ways to write that problem. Let's do. Okay. Yes, I did have to think about this. So we are going to do something much simpler. We are just going to do D is in equilibrium with E. These are both aqueous. Two things. That's all I got. All I have is two things. We are going to give a K expression of 9.8 times 10 to the -4th. I don't even know. And I am actually just going to leave things with no exponents for right now. And I'm going to tell you that the initial concentration of, one moment, please, I'm thinking, of D is 0.1, and the initial concentration of E is 0.001. Yeah, that's what we're going to do. So again, I know that this is a bit simple. This is a bit simple because I want to make sure that I can solve this problem. And when I make things up from scratch, sometimes I make it too complicated. So I now have initial concentrations for both. I realize I didn't write a problem out, but we're just going to go ahead and use my ICE table. So I have a value for K, and we're going to go ahead and say that the goal is the equilibrium concentration of D. That's my goal. We'll go ahead and solve for both of them. And the equilibrium concentration of E. We're going to go ahead and solve for both of those. So right now, I don't actually know which way the reaction goes, right? I have no idea. So what we're going to do is we're going to solve for Q, because Q is products over reactants. And in this case, there's no exponents. Again, I did simplify this so I could actually solve it. So Q, all I'm going to do is do my initial concentrations. So Q is basically the initial concentrations of just whatever you have. So in this case, I have 0.01. Sorry, 0.001 divided by 0.1. I'm going to plug this in my calculator just to make sure I don't mess up. And that gets me a value of 0.01. So now I have a K value and I have a Q value. When I have my K is less than Q, so in this case, my K value is 9.8 times 10 to the -4. My Q value is 0.01. That K value, again, writing it out without that, is still less than Q. Because my K value is less than Q, I'm going to assume that this is going to go back towards the reactants. I know that for a couple of different reasons. One, we're going to start with, one, because everything is about products over reactants, a larger number means more products because the product goes on the top. The product goes on the top part of my fraction. So my K value is so small that it's telling me that it is reactant favored. My K value is so small that 10 to the -4th tells me I should have mostly reactants by the time that we're finished. My Q value is larger than K. That says Q is like, I found all this stuff. It's actually kind of a lot of products compared to K. So since there's a lot of products in comparison to K, this is going to go back towards the reactants. Now, I will tell you the other way that I know this is because one of the, I forget if it was an SI or a PLTL leader now, taught me that if you put these in alphabetical order, so the K goes on the left, and the Q goes on the right, as long as you set it up like that, the equality sign will basically point in the direction that the reaction goes. So when you look at this less than sign points to the left, which means that this is going to be a head towards the reactants. So that's the other way that I know. You do have to make sure that you put K on the left and Q on the right for that to work. So I like to think about this as being in alphabetical order. I like to think about this as being in alphabetical order. So therefore, I'm going to expect this to go back towards reactants. That means I'm going to expect a minus sign where my product is, a positive sign where my reactant goes. So continue to fill out this table, 0.1 plus x, 0.001 minus x. I went ahead and did this in such a way so that I don't have to worry about thinking about the approximation method. Since I don't have to deal with any sort of exponents, I can just solve this. A word to the wise. Part of the idea of the approximation method is that k is small in the direction we're going. So first of all, we have a problem because k is small, but so is the initial concentration of E. Then the other thing is, if I really want to talk about the change being, is the change small? The problem is K tells me that I'm reactant focused. I'm reactant centered. I should have a lot of reactants. And that's the direction the reaction's going in, back where I should have a lot of stuff. So I'm not confident that we could use the approximation method. If I wanted to double check, what I would actually need to do is rewrite this so that I could address which direction or is K small in the direction I'm going. So I could go ahead and reverse the direction of this. If I do that, then K is 1 over 9.8 times 10 to the negative 4. So I could do this with a new K value. And again, I have to do this because part of the idea of thinking about K being small is thinking about, is my change going to be small? And the hard thing with thinking about, is my K value going to be small, is do I actually expect that change to be small? Okay, minus x where the E goes, plus x where the D goes, 0.001 minus x. And so basically now what you should be able to see is that where that changes, now my K value is large and now who knows. So I don't actually know that this is helpful for most of y'all. I honestly set this up so I wouldn't have to think about the approximation method. So, but if we wanted to do it so that you are always having products be positive, you could reverse the entire reaction should you want to. I'm not going to do it that way though. I'm going to continue to solve just using this ICE table that we already did. So that still means I'm going to use the original K value, but I'm not going to use the approximation method. We are just going to algebra this to death. So I'm going to use that 9.8 times 10 to the negative 4 is equal to products over reactants. That's 0.001 minus x divided by 0.1 plus x. And now we solve. So one of the other comments that I've gotten is the general sad face about the amount of algebra. Keep in mind that while the questions that I've been getting deal with the ICE tables and algebra, so I have been doing a lot of the algebra, there are, again, other problems that we will ask besides this. So just keep that in mind as we go through. Which way am I going to go? We're going to go and just get all the x's on the left. So this then becomes 1.00098 x is equal to 0.001 minus 9.8 e negative 5, 0.123902. 2, 3, 9. Technically, 1. So now I have a value of x, and my goal was to figure out my equilibrium concentrations. So I can go back to my table, and what I should be able to do now is take 0.1 plus 1, 2, 3, 9, and get an equilibrium concentration for my new amount of D and an equilibrium concentration of my E. 1, 2, 3. 1, 2. Right. This is the part where I am glad we have calculators just because 1, 2, 3, 9. Scientific notation would help me out a lot. 9.9 times 10 to the -5. Shoo! So again, we can always go back to the original ice table to fill things in. So keep in mind that if we are going to have y'all decide which direction the reaction goes, that something with relatively few exponents or things that are dealing with squared terms is kind of where we have to go. So some of that math has to be relatively simple in order for you guys to be able to calculate it. So I know I picked relatively straightforward numbers and relatively straightforward chemical reaction to start off with, but I did do that one mindfully so that it would better mimic what's going on, because I need to be able to solve all the algebra, and so would you. So basically I used Q is what I used. I used Q compared Q. Okay, so since it's about 4 o'clock, let me go ahead and ask for questions again. So any questions so far?
Yes, there's 2 more.
Okay.
Can you please go over oxoacids and carboxylic, I'm sorry,
Okay.
acid? I got 0.007305 from graphing calculator. Is that okay?
So if we're gonna ask, is the graphing calculator okay? Come talk to me in office hours. If we're gonna have the graphing calculator question, we have to sit down and do this one together. We are not gonna do this over the exam review because I can't answer that question. So I'm just gonna tell you straight up that that's an office hours question. I respect the trying that out, but I'm not going to do that here, mostly because what will happen if I do is we'll get about 4 different people all doing it on their graphing calculators, and then y'all will start to just argue with each other. And that's really awesome for PLTO, and that's really great for an SI session. That's not going to get us super productive in a review session where I can't sit down with you. So I'm going to tell you that that's an office hours question. Okay. So I see the oxoacids and the carboxylic acids. One of the things I'm going to remind y'all about.
Sorry, there's a couple more.
Yeah.
Okay. So, can you go over the equations we are going to use and how to use them for acids and bases?
Okay.
And then can you go over manipulating K expressions? And that should be it.
Great.
Sorry for interrupting.
Oh, no, you're fine. Okay. So one thing to remind y'all, in the 701 section, there is a tab that just says videos, a folder that just says videos. And in there is one for every single chapter, including acids and bases. And so should you guys want those videos about oxoacids Those do exist. Those do in fact exist. They have been posted since the beginning of the semester. So just keep that one in mind. If there are other things that you are interested in, there are a variety of different ones already posted in here with different titles. So those do exist. I will try to get to it still, but again, just a reminder that there's a whole set of videos already hanging out in there. Okay, so I know I didn't really answer the graphing calculator question aside from say see me in office hours, but I'm going to give that one a check mark. We're going to go ahead and deal with Le Chatelier's principle and temperature and equilibrium shifts in general. So first of all, dealing with Le Chatelier's principle. Le Chatelier's principle is the one that basically says, if I have a bunch of stuff and we change something, tell me what happens. So if this is my equilibrium and I tell you that we are at equilibrium, everything is happy, everything is calm, that's a smiley face. Then something changes. Then we do something like we add more C. So the concentration, and we're going to make these all aqueous again. Aqueous, aqueous. Then I add more C, or the concentration of C goes up. What happens? So when we talk about Le Chatelier's principle, which I might misspell, there's we're basically saying if we were at equilibrium, but then we change it, what happens? So it was at equilibrium, then we add more C, we increase the amount of C. Keep in mind, essentially what we're doing is we are changing Q. So if I have more C, Q is again my products over my reactants. So if I add more of a product, then what should happen is I should get a Q value that's bigger than K. So if I add more C, I should wind up with a reaction that needs to shift back to the left to deal with all the products that suddenly got dumped in there. Or that if I was at equilibrium, but now the number of products went up, my Q value is now larger than K. So since my Q value is larger than K, I should see a shift back to reactants because my K value is smaller than Q. So that's Le Chatelier's principle in a nutshell, is what happens when you change things. There are a whole list of things we might potentially change. One of them is just adding products or taking them away, or adding reactants or taking those away. And that's all K and Q. It's all K and Q. So if I add more C, I should shift to the left. Same idea if I add more A or B, I should see a shift to the right. Because if I'm adding more reactants, I should see a shift towards the products. Add more C, I shift left. And anytime we say shift left, we mean towards reactants. Anytime we say shift right, we mean towards products. So that's another thing to keep in mind is that left is where your reactants are. Right is where your products are. So even though I understand we could say shifts towards reactants or shifts towards products, we usually just say shift left, shift right. My class, I think I already did a speech on this one, but it was super common for me when I was teaching this, that I'd actually have a little thing that just said R in equilibrium with P, which is R is in equilibrium with reactants and products, and then left and right, so I wouldn't get it mixed up, because that's actually kind of difficult for me to do. It just is. I'm not dyslexic. But there's a couple of different things that I was taught in my life that has made my lefts and rights surprisingly difficult for me to identify. Even though dyslexia is not a problem that I suffer from, I do suffer from left and right problems. Just left and right. Just left and right. Um, so, um, oh, so again, so there is a whole list. So adding more reactant, shift to products or shift to the right, adding more products, shift to the left, shift towards the reactants. We could also do things where we take away products or reactants. That's a very similar idea. Or if I still have the same idea, aqueous, aqueous, aqueous. I could remove A. If I removed some of the reactant, I would expect a shift left, essentially to replace it. If I lost some of my reactant, I would expect the equilibrium to shift back to replace what was lost. So therefore, if I removed C, I would expect a shift right to, again, replace what was lost or replace some of the product that was lost. I apologize for those of you that might be able to watch my face and see me be distracted. My family is texting about my dad who is having some health struggles, so I am a little distracted by that. I should put my phone away. But the actual question that was asked was about temperature. So since the actual question that was asked was about temperature, let's go ahead and talk about that. But talking about shift left and shift right for products and reactants is what we need first before we talk about dealing with temperature. So we're going to use the same equation, but now we're going to go ahead and add some information. And we are going to say that the delta H for this is -10 kilojoules per mole. Why not? Because of that, that's an exothermic reaction. Since that's an exothermic reaction, I can treat heat as if it was a product. I have an exothermic reaction, and therefore I'm going to treat heat as if it is a product. So now, when I talk about shifting, I could go ahead and change one more thing. Instead of just saying I could add or remove a product or a reactant, I could now talk about heat in the same way. So I could go ahead and do things like place reaction in an ice bath. I'm making it colds. I'm making the reaction colds. That's what an ice bath does. Ice is cold. I put it all in an ice bath. I make the reaction cold. Because of that, since I'm treating heat like a product, making the whole reaction cold is as if I was removing the heat. So I would expect this then to shift right, or to shift, I'm going to say here, towards the heat, since this is an exothermic reaction that happens to be on the right. So you put the reaction in ice bath, because it's an exothermic reaction, that's going to be towards the right. That does mean that if I had a different reaction, we're going to deal with G in equilibrium to L. Why not? And my delta H now is +7. That means that this reaction is endothermic. Heat becomes a reactant. Now, if I place this reaction in an ice bath, Now I would expect this to still go towards the heat, but the heat now is on the reactant side. So now this is going to go, it's still going towards the heat, but it's an endothermic reaction. That now is on the left-hand side, or a shift left. So changes in temperature depend on whether your reaction is endothermic or exothermic. So unlike products and reactants that are locked in place, their products are always on the right, reactants are always on the left. The thing with temperature is that heat, where that is, depends on if your reaction is endothermic or exothermic. And that will determine where things go. Likewise, for my endothermic reaction, I could also say that the temperature increases. If my temperature increases, then I would expect this to act as if I was just adding more reactant, in which case I would expect this to shift to the right. But again, that's for my endothermic reaction. So the temperature one gets a little bit more complicated because you have to do that analysis of where does the temperature go? Where does it belong? And that's going to depend on if it's an endothermic reaction or an exothermic reaction. The other thing I will say about changes in temperature. When we study Le Chatelier's principle, we go ahead and just include it as a product or a reactant because honestly, it works beautifully. It works absolutely perfectly. And if the goal is, here is the way we've changed the reaction, tell me what happens. Treating heat like a product or a reactant is perfect. It works great. It's beautiful. Works every time. The thing to keep in mind is K is temperature dependent. So while treating heat like a product or a reactant will get you the correct answer, which is why we teach it. Because even if I had to figure this out, I would still use this trick because it works. K is temperature dependent. What's really happening is exothermic and endothermic reactions change in different ways when the temperature changes. And that's actually why everything works the way it does. So temperature change is not a K versus Q thing. Temperature change actually changes your equilibrium constant. So when you're talking about a temperature change, you're actually changing your value of K. When you're changing the temperature, you are actually changing your value of K. Predicting that, we are still going to use the trick of treating heat as if it was a product or a reactant. Because again, it works beautifully without fail. But K is actually temperature dependent, which means your K value is changing. That is why in the chapter where we talk about KW, that is why we have this whole table dedicated to talking about what happens when K changes. Nope, where's my OneNote? But that really is why when we talk about KW, we basically have an entire table to say, when you have this temperature, this is the K you expect. When the temperature is this, this is the K value you expect. And you can look at how those things change. So K is temperature dependent, but when we solve for, are we shifting left, are we shifting right, we just treat it like a product or a reactant. It works beautifully. That is still how I teach it, because it still works great. Okay. So I think we've done Le Chatelier's principle and temperature. I think we've done changes in composition. and equilibrium shifts because we did products and reactants. What I'm going to do is I'm going to go ahead and scroll. I'm scrolling back through my own notes real quick, and I'm like, what else is in? So factors that affect chemical equilibria, add addition of a reactant or product, removal of a reactant or product. We did those, and we did change in temperature. We did not do change in volume. So we can talk about change in volume since that's the only other thing that does change your Le Chatelier's, that does affect Le Chatelier's principle, is change in volume. But to do a change in volume, I need a different kind of reaction. Because they need to be gases. I need gases. Gases. As a gas. It's a gas. Sorry, this is the part where my background in biochemistry shows a little bit. My brain is just like, no, everything is aqueous. Everything's in a liquid. Gases. Gases aren't bad. No, flip those around. Make it something that's real. There we go. Like that. Also a gas. Okay. So the last thing, which is this. So what this is this is going to be, we're going to go ahead and talk about changing the volume. So if I decrease the volume and I have a bunch of gases in here, 1, 2, 3, 4, 5 gas particles, and I decrease the volume, 1, 2, 3, 4, 5 gas particles are still in there. What has happened when I decrease the volume is I have increased the pressure. When I decrease the volume, I increase the pressure. When this happens, when I decrease the volume and increase the pressure, then we move to fewer moles of gas. I move to fewer moles of gas. It is essentially trying to relieve the pressure. So for this reaction that I have on the screen, if I'm going to say that we are going to decrease the volume, I would here expect a shift to the right because I have 2 moles of gas on the left and I have 1 mole of gas on the right. So if I decrease the volume, which increases the pressure of my gases, that's going to be a shift to the right. As usual, this does mean we could think about things in other ways. We could also talk about the volume increasing. If the volume increases, then my pressure decreases, and I go, and here I would shift to more moles of gas, which here means the left. So things to keep in mind, anytime we deal with Le Chatelier's principle, it's going to be a bunch of opposites. We could add things on the left, we could add things on the right. If we can increase the volume, we can decrease the volume. If we can decrease the volume, we can increase the volume. And notice then that this is what is a shift to? It's not just left and right here, it's a shift towards where the moles of gas are. So either it's a shift towards fewer moles of gas if the pressure has increased or if that volume has decreased, or if the pressure has decreased, we're shifting towards more moles of gas. When I say pressure, part of the reason why this says the volume decreases is because when we talk about the change in pressure, this needs to change the partial pressures of the gases in the reaction. Because changing the volume really affects Q again. Changing the volume actually affects Q. Because what has really happened here is, I'm going to get my reaction correct. When I'm thinking about this reaction, I am in fact thinking about changing my value. So I have a value of K where it's the partial pressure of N4O2 divided by the partial pressure of N2O squared. So that way, when things are changing, this is really then talking about my pressures changing. So when I'm dealing with changes in volume, the goal is to think about changing the partial pressures of the gases. And again, we can still just use fewer moles of gas, more moles of gas, and all of that still works beautifully. But you have to keep in mind that what we're changing is we're changing the pressure of the actual components in the reaction. Because those are the things that do change and cause shifts in there. So I know that's a lot of opposites. I know it is. So one of the things to keep in mind with Le Chatelier's principle is we have a tendency to ask one question about Le Chatelier's principle. So it's still worth knowing because we do ask about it. But we have a tendency to ask more questions about pH and POH and all of that jazz. Okay. Since we're coming up on 4:30, are there any other questions in the chat right now?
No, ma'am, not that I can see.
Cool, thanks. Okay. So let's go ahead and talk about elementary steps and differences in catalysts. So first of all, you say differences in catalysts. I'm going to assume you just mean things about catalysts in general. So for catalysts, we really only covered 3 kinds of catalysts. Homogeneous, heterogeneous, enzymes. We also covered homogeneous and heterogeneous equilibria, which is part of the reason why I'm reviewing this. So catalysts can be homogeneous. This just means the same phase as the reaction. So homo means same. This could be heterogeneous, which is different phase. Phase here means solid, liquid, gas. Aqueous. Aqueous. Enzymes are biological catalysts. My favorite. So enzymes are biological catalysts. Enzymes are going to do a variety of different things. But basically we think about them as like molecular machines in your body that help reactions happen. So enzymes are just biological catalysts. We're just going to go with that for the purposes of this class. A heterogeneous catalyst. The reason why this one is important is because there are times where you have a reaction that's all gases, but your catalyst is like a piece of metal and is a solid. So we do make that distinction between homogeneous catalysts where everything's in the same phase versus a heterogeneous catalyst where they're different phases from each other. So those are the 3 types of catalysts. The other place where these come up is in that question about elementary steps. So when we think about elementary steps, now I wish I had prepped one of these in advance. One moment, please. Brain is braining. We'll make this kind of straightforward. So I could say this is a reaction mechanism. If I tell you that, then you get to assume that these are elementary reactions. I could also tell you these are elementary reactions, and then you could know that these are elementary reactions. In here, I could ask you different things. So I could ask you for things like, what is the overall reaction? So for the overall reaction, what I'm going to do is add together my two reactions together. So I do basically have A plus B plus C goes to B plus C plus D. And what you might notice is I've got two different things that cancel out. My B's cancel out and my C's cancel out. My overall reaction is just whatever's left, which is A goes to D. So that's my overall reaction. But we have a tendency to ask more things. So we might ask for things like what the intermediate is and what the catalyst is. The thing is that B and C are our contenders for intermediate and catalyst, but they do two different things, and this is the part that's important. B is there in my reactants from the very get-go, so I can physically add it in myself, and then it shows up again in the end. We did also cancel it out, which is important, but because B is there in the beginning and it shows up again in the end, B is the catalyst. A catalyst is something that I, as a human being, as a scientist, can add to this reaction. A catalyst is something I can control. Catalyst is something that I get to mess with. I am in control of a catalyst as a person, as a scientist doing a reaction. I'm in control of the catalyst. I can add an enzyme, and it had better be there in the end when we're all said and done. On the other hand, an intermediate is something that shows up and gets used. I don't control the intermediate. The intermediate here is C. The intermediate is something that appears. It sometimes is stable enough that you can measure it, but it is very rarely something that you can actually add. Sometimes you can, sometimes you can't. It depends on what it is and the reaction. So the intermediate is something that if you're really lucky, you can observe it. But sometimes you can't do that. I am sorry that I've lost my AirPods and you can hear my dog coughing. He has gone to the vet for that, by the way, if you can hear him. So we are aware of his issues. He is on medication, just in case you're concerned. We monitor that pretty closely. So my intermediate is something that appears. So it's something that shows up in the products first and then gets used in the reactants. A catalyst is backwards from that. A catalyst shows up first as a reactant and then reappears in the product. Since we've done this much, because I have the presence of a catalyst, I could actually ask you for what is the rate law for the overall reaction? Here's a weird thing about catalysts. Because catalysts control the rate of the reaction, the rate determining step has to be the one with the catalyst. So even though there's no fast and slow written here, the rate determining step has to be the one with the catalyst. We already identified that we have one. So I can actually write the rate law for the overall reaction. Even though it might look a little weird, the rate is equal to K times A times B. Or this is the rate law for the first elementary step. But in this case, I'm allowed to do that because we know that B is a catalyst and the rate law has to contain the catalyst for the overall reaction. So catalysts definitely do some special things, especially in elementary reactions. One of the other things, since we're talking about all of this, that I am just going to draw ever so briefly. I had a two-step reaction mechanism, so we'll go ahead and draw a two-step mechanism. So for example, this could very well be the reaction mechanism to go with what we just did. I have two steps. I have two humps, step 1 and step 2. I have my reactants here on the left. I have my products here on the right. I have my intermediate down there in the middle. I have things like activation energy that I can draw in. All sorts of things. Activation energy 1, activation energy 2. So dealing with reaction coordinate diagrams is also part of what's in chapter 14. So mostly through the graph in there to remind you that this is another way that we can either give you information, another way we can ask you questions. Hold on. Intermediate. So mini component parts, but not a bad quick version. Okay, let's scroll back to take a look at my stuff. All right, we talked about elementary steps. We didn't talk about fast and slow though. I'm a little sad about that. Hold on. So where you can see my blue line here is longer. My activation energy 1 is bigger than my activation energy 2. This here means that step 1 is slow. We therefore call that the rate determining step. So we do in fact refer to that as the rate determining step. So first step is slow because the activation energy is greater. Just to keep in mind when we are doing things like that, dealing with activation energy does in fact mean I can do things like this. Oh, that's kind of weird. But keep in mind when I say activation energy goes from wherever I'm beginning to the top. So wherever I'm beginning here to the top, from wherever I'm beginning all the way to the top. I can't even draw that straight line. I'm sorry. There should be a straight line in there. Let me try that one more time. If I draw it from top to bottom, it'll go better. There we go. So realize here that this is the third step and this is the slow step because of my activation energy 3 is the greatest. I have to admit, I don't know if 1 or 2 is bigger after that, but one of the mistakes I sometimes see people make is they'll just try to look for like which hump is highest, and that's not how this works. We're absolutely trying to think about the activation energy of each one of those, and sometimes they're the same. So this other one that I drew, the first step definitely has the highest hump. The first step also has the greatest activation energy. It's that line underneath. Here, though, that's not true. Here, step 3 has the greatest activation energy. Step 2 is taller. So just be aware that that third step with the greatest activation energy is going to be your slow step, even though it's shorter across the top than the other one. So steepest gradient, highest from bottom to top, highest, not draw a line across the top, highest, but from bottom to top, highest, from bottom to top, highest. Okay. I'm going to save oxo acids. And I'm going to save oxo acids for a reason, because if I'm going to do oxo acids, I also have to do binary acids. Because you can't really do one without the other. Ironically, they are also easy to confuse between the two of them. But this conversation takes me about 20 minutes, which I guess technically I have, but let's actually go ahead and deal with manipulations of K, because I can definitely do that. All the equations for acids and bases, I will go ahead and just flash those up again, because basically all the equations that y'all need for acids and bases were actually already on that sheet. So this pH and pOH and KW and pKW. Those are your equations really for your acid base chapter. That's what you need. About the only other thing that you might need in there, which I don't think this is going to go on your potentially useful information, but is what KW is. So KW is equal to 1 times 10 to the negative 14th at 25 degrees Celsius. I'm just going to go ahead and say now, I don't remember if it goes on the page or not, so I'm just going to tell you now to have this memorized. Because that way you're going to know that pKW is equal to 14. So that way at 25 degrees Celsius. So that way you'll know that pH plus pOH is equal to 14 at 25 degrees Celsius. And that is really useful. Useful now, useful later. pH and pOH have to do with the hydronium and hydroxide concentrations and deal with negative log. But I'll do more about those in a follow-up video. Let's just do manipulations of K. So we're going to do manipulations of K. There are 3 of them. We actually did one earlier in this video. So the first one is reversing the direction. So this is one where if I have A is in equilibrium with, we're going to do this 2A is in equilibrium with B, and I tell you that the K value is, I'm going to go with 20, but I reverse the direction of the reaction, and I now tell you that now I would need B in equilibrium with 2A. What is my new K value? New K value is just 1 over 20, right? I have flipped products and reactants. When I talk about my definition of K being products over reactants raised to their exponents, when I reverse the direction of the reaction, I am changing those two things. So I can solve for my new value of K by putting 1 over my original value. So that is reversing the direction. So reversing the direction is just 1 over K. So that's one manipulation. 1 down, 2 to go. The other one is changing coefficients. If we change coefficients, so let's go ahead and just make this 4A in equilibrium with 2B. If we do that, then what we are doing is we are in fact changing our coefficients. Since we're changing our coefficients, what's going to happen then is I can take my original K value, and then I'm going to just take whatever happened, since from here to there was multiplying times 2, I'm going to take and make that multiplication into an exponent, just like we do in K's expressions. So my original K up here was K is equal to the concentration of B divided by the concentration of A squared. Now that I've multiplied all of those coefficients by 2, my new one would be K is equal to the concentration of B squared divided by the concentration of A to the 4th. So that changing coefficients of the reaction changes the exponents of K. Changing the coefficients of a reaction changes the exponents of K. So that's what I'm doing here, is I'm figuring out however we manipulated that and putting that exponent there. We could do it to a completely different factor. So if I had my 2A goes to B, I could very well have this be 12A in equilibrium with 6B, in which case what I would need to do is I would need to take that original K value of 20 that I had. And since now what's actually happening as I go from 2A goes to B, now this is a factor times 6. Now I would raise this to the exponent of 6. So whatever that factor is what I'm using for my exponent. Likewise, I could also do this if I went to A goes to 1/2 B. I could also raise my K value to a fractional exponent. I can do that too. So keeping in mind, works for multiplication, works for division, but again, division here is really going to be multiplying by 1/2 or multiplying by 1/3. But I can also use fractional exponents to do that. So that was 2. So for manipulations of K, we can reverse a direction, 1 over our K. We can change the coefficients. That's going to be using exponents to deal with whatever that was. Oh, good. I made all the balloons go in teams. If you really care, if you're watching the recording, you can rewind the recording and see my little profile. It's adorable, and I get annoyed by it every single time. So here's my original equilibrium. Then if I had one that was B in equilibrium with 3C, and I told you that this K value is 0.01, I could add these reactions together. So then my B's will cancel out. I would get 2A is in equilibrium with 3C, but for my K values, I'm going to multiply those K values. So if I wanted the new K value for this, I would have to multiply 20 times my 0.01 to get my new value. Of 0.2. So if I'm going to deal with adding together reactions will make me multiply by values of K. So a lot of the manipulations of K require you to think about how the chemical reaction is related to the K expression, because it's never the same. Reversing a direction means I put 1 over K. Changing coefficients, which is multiplication, means exponents. Adding together means I multiply my K values. So just keep in mind as you're looking at manipulations of K, this is all about how the chemical reaction relates to my K itself. And again, usually it's never the same. It's never the same thing. Always something a little bit extra to deal with K. Are there any other questions out of the chat so far?
Yes, and there's two more.
Great.
What is the activation energy for the reverse reaction on a graph?
Cool.
And can you go over an equilibrium problem where we have to use a quadratic equation? That should be all.
Fabulous. Okay. So the activation energy for the reverse reaction, this one I can definitely do in 10 minutes. Let's go ahead and bring back any of these. Which one? There we go. So what I'm going to do is I'm going to take this one I already did, and with any luck, copy it. Yay, copy it. And put it over here. And now I'm going to hopefully erase just a couple of random pieces. I can't get rid of that C. That's okay. So here's the deal with a reversed reaction. With a reverse reaction, some of these things, so I have my original here on the left, and now all we're going to look at is we're going to look at what happens when you reverse a reaction. So here's the exact same graph, copied and pasted, so that we can make sure we're talking about the same graph. Ah! Oh, Microsoft. Oh, OneNote. Okay, so here's my graph on the left. Here's my graph on the right. What we're changing now, though, is we're going to think about this as a reversed reaction. That means that where I had my products here on the right, that's now going to be my reactants. And this thing on the left here will now be my products, as I'm going to go in the reverse direction. So originally here on the left, we went that away. Whoops, that's too big. Can't actually read what I'm doing. We originally went the reaction progress from left to right. Now we are doing reaction progress from right to left. So this is the reverse reaction. So that means, since I'm doing a reverse reaction, I need to think about my activation energy. That means, though, I'm still starting from wherever my reactants are, and I'm going to wherever my transition state is. That's still true, but I'm reorienting where my products and reactants are. So on the left, when I had reactants on the left, I started with the reactants. Now that my reactants are on the right, I still start with the reactants. That's still true. But how this, what that does to the activation energy is very different. Similarly, if we could go ahead and then look at my activation energy for my second step on the reverse reaction, I start at that intermediate and I go to my transition state. So I still have two distinct activation energies, but they are different because I'm going now from right to left. So when you reverse a reaction and you want to talk about activation energy, my advice to you would be to make sure you're labeling your reactants and products and just keep in mind where you're starting from, because the definition of activation energy is still the same. We're still starting on wherever we start from to the transition state is still the activation energy. Still true. We just begin from somewhere different, and that makes it different. I will go ahead and put a little label here for the transition state. These are both transition states. transition states. So the top part, the top of the peak is always the transition state. That is a different thing from the intermediate. So if your reaction ran in reverse, you would be considering different activation energies because there's different activation energy barriers to go back the way you came. But a good question. A good question. What's the other thing? Oh, the quadratic. I cheat when I have to do quadratic. So when students ask me to do the quadratic, I always work it out in advance. I don't know if you guys have noticed, but when I have to talk and write at the same time, I am more error prone. So I won't do a quadratic off the top of my head anymore, mostly because what undoubtedly happens is since I'm trying to talk and write at the same time, I usually make a mistake. I don't know. I've been doing this for a really long time. You would have thought I would have mastered talking and writing at the same time. I haven't done it. So I will definitely do a quadratic in the follow-up video, but I will not do one live. That one has never ever gone well for me. I've done it before. It was somewhat tragic. Okay, binary. That's it. So anything else I can answer in 3 minutes? There's not. I can't answer any of these in 3 minutes. I'll talk about pH real quick. So one of the equations with acids and bases that we can go ahead and deal with real quick is pH. I know I'll probably have to reintroduce it anyway. So one of your equations is pH. Looks like this. Also, though, looks like this because we are going to be assuming that the proton is the same thing as a hydronium ion, because this is true as long as we are in aqueous conditions. As long as we're in acids and bases, we are in aqueous conditions. So you're going to see a proton interchangeably with a hydronium ion over and over and over again. One of the things that you are going to need to do is locate where your log button is on your calculator. Since last time we did natural logs and dealt with integrated rate laws and natural logs, you likely have found it before. But keep in mind that in order to deal with these equations, well, these equations are on your potentially useful information page. Getting out of them is actually not. So if I wanted to reverse this, I have to have the negative pH is equal to the log of my H3O plus, or 10 to the negative pH is equal to the hydronium concentration. So do keep in mind that the 10 to the negative pH is not listed on the information sheet because you should be able to go in and out of them. Just like we didn't give you guys like how to undo the natural log, we're not giving you how to undo a regular logarithm. So just keep in mind that being able to both go in and out of those are important. And I will be doing more with the equations from chapter 17 in the follow-up video. Are there any other questions out of the chat for right now?
No, ma'am.
Okay, cool. Then we are just about at 5 o'clock. I'm going to scroll back up in those last couple seconds to show off what is covered on the exam. So a reminder that we are covering that last little bit of chapter 14, chapter 16, everything from the notes. If you're in the textbook, there is a section that we have skipped over. If you're in the notes, then it's everything in the notes. And then in acids and bases, we have kind of an odd stopping point. Again, if you're looking at the book, the notes, again, will cover well where we're stopping in acids and bases. And then there's also your end chapter problems to help you guys out. But it is 5 o'clock, so everything else is going to be saved for the follow-up video. That's it.
Thank you. If there's nothing else, I'll go ahead and end the event now.
Perfect.
Okay, thank you so much.
Thanks.
Bye.
Yeah, thank you, Dr. Taylor, as always.
No problem.
Thank you.
No problem. Bye, guys.